Hello, everyone. Welcome back. It's April the 7th, and we are very close to the summer. This is Aditya from Skive and Robometrics Machine, and you have reached the AI Tech Talk Live. Today, we'll be covering GPU versus CPU for AI. Which one is better? When do you use when? Is GPU better than CPU? Is CPU better than GPU? Or there's something else? Just as a background, we usually cover topics in artificial intelligence. In the last couple of weeks, we have been covering advanced AI technology aspects. So we covered deep learning, we covered supervised learning, we covered unsupervised learning. We had also covered reinforcement learning. In the last couple of sessions, we covered artificial general intelligence. Last week, we started our sub series on AI and semiconductor. So this is just a continuation of that. Our first question is there an apple to apple comparison when we talk about GPU and CPU? You're trying to compare two different things, but if one is totally different than other and it's a totally different use case, then how can you compare it? The answer is yes. When we say artificial intelligence, most typical workloads you can think of or applications in simple language is deep learning and specifically supervised learning, where you have the training phase and then the inference phase. In simple language, inference is when you execute and get the answer, and training is when you train the system to build a model that's used to execute or to infer. And that's where GPU versus CPU lies. GPUs in general tend to be better for training, and that's because training involves a lot of these matrix multiplications, and that's what training is from deep dive from a code perspective. There's lots of these matrices with a lot of these numbers, and you are multiplying it. And GPUs traditionally, how it was built by Silicon Graphics a long time back, and then NVIDIA took over the use of GPU for a totally different thing with artificial intelligence. It's based on the same thing, that for graphics you need floating point calculations, and GPUs are great for that. And that's where came NVIDIA, who used this feature of floating GPUs being very good in floating point computation for training. So GPUs are great for training specifically. CPUs in general are not that great for training per se. Now, for inference, it's an interesting ball game in the sense that if you're talking about inference in the cloud, either a GPU or a CPU can actually work. If you're talking about inference at the edge, so if you're talking about inference that's happening, for example, in a cell phone or an IoT device, CPU is usually a better compromise because you don't need that much floating calculations for that. Our next question is the selection dependent on cloud computing and versus edge computing? Absolutely, and I just covered that a little bit. The four KPIs, or four parameters or key performing indicators that comes into picture when you're talking about edge computing. Speed, what is your throughput? Latency, you usually will need very low latency when you're talking about edge computing, so facial recognition, for example. Efficiency, how much calculation or computation can you do per watt of power, because edge computing usually involves computation on the edge where you don't have a lot of power. And lastly, accuracy. If you're talking about inference especially, a lot of the time you don't need 100% accurate answer, because what we're talking about when we talk about deep learning, for example, we're talking about more probabilistic results, so you don't really need that much accuracy. And for all these considerations for edge computing, a CPU tends to be a better way to go about it. But as we have seen that a lot of the system on chip architectures or chips include both CPUs and GPUs on the same device. So they will have a few ARM cores, plus they will also have a GPU or two. And for example, for running some of the training, you could use a GPU for running some of the video specific applications. For example, running your screen, you can use a GPU. And that becomes very interesting in the sense that that's where you go deeper into how you could build a custom-based ASIC. And we won't go into details on a custom-based ASIC, but we'll probably cover that next time. So I will just give two examples of custom-based ASICs. One is the Tesla's fully autonomous driving technology on a chip. They came out with that about a year back, and now they're coming with the next version of that, where it has everything needed for autonomous driving on the chip. The heart of the chip of autonomous driving is there in the chip. The second would be that a lot of you already know about, which is A12 or A14 Bionic. A14 is the latest chip that we have in our latest iPhones, and that includes ARM 64 cores as well as a GPU for various things. It actually even includes a neural network core to do neural network specific computation, facial recognition, for example. Our next question is interesting. So the gentleman is talking about how is a Google TPU different from a CPU or a GPU? A couple of years back, when Google was trying to design the next architecture for the internal data center, Google, till 5 years back, was mostly a cloud-centric company that provided you web application. Google Search is there, Google Map is there, Google Translate is there. So their intent was to build a better architecture that could run their internal data centers much, much better. That's where they came with what's called a TPU or a tensor processing unit, with a very minute change in the overall computation or how you do computation. What they did was they reduced the floating point architecture of the processor from 64 to 32-bit. So you may have learned this in your high school in your mathematics class, that you have in a floating point number, you have the fraction or the mantissa and you have the exponent. So what they did was they reduced the number of bits for that. And what that resulted is that instead of a 64-bit instruction set, now you have a 32-bit instruction set, which means they reduce the number of spaces in instruction needed for floating point. And of course, reducing the precision, that's what it's actually called. Sometimes the 32-bit precision, or float 32-bit is called single precision. What they did was that reduced, obviously, the accuracy of that computation. So now you will have less accuracy, but that is okay. That's how training is done, where you don't need deterministic answer. It's probabilistic anyways, because you're calculating those ways through these by multiplying these numbers, lots and lots of these numbers as matrices. There was another interesting thing that happened when you reduced the number of floating point digits. Now you need less power to do the same computation. So you could do the same computation faster and in less power. And that's where a TPU was born, where now you could do the same number of computation in much less time because you're doing simpler computation and in much less power. What that also means is that the same core or a TPU could have much more computation per core. The computation that the TPU, even a TPU 1.2, and I believe the latest one is 3.0, was so much that they need to liquid cool these GPUs because it was running so fast, so many computation happening per second. And that's what a TPU is, where we were able to get a processor to run much faster in less processing power. And interesting enough, it did much better than a GPU or a CPU. Now you will assume that by reducing the floating point, a TPU is only good for inference when it comes to AI. And that's how cleverly Google marketed TPU as well. They said the Google TPU 1.0 is great for inference. And then a year or two later, they said, our TPU 3.0 is also great for inference, not just for training, just like a TPU 1.0. And the only difference was marketing. And a year back, they also came up with the TPU on the edge, where you can use the same TPU on your edge computing device too. And these GPU was doing great. And in addition, Google usually have a great tradition of having open source software. Every one of us, if you have heard about TensorFlow, and they optimize the compilers and tools to make TensorFlow much more optimized for Google TPUs. Another interesting aspect of a Google TPU was that, and it still holds true, that because you actually change the instruction set from 64 to 32-bit, now your external internet world is totally foreign to you, because that doesn't really run on TPU. It still runs on CPU, in some cases GPUs, which still follow the 64-bit instruction set. So even in a TPU-based Google Cloud Center, they actually still use Intel CPUs, which actually is the interface with the outside world. But internally, they will actually use the TPUs. With that, I will close for today. Next time, we'll be back here again, and we'll be talking about custom ASICs and SoCs in context of artificial intelligence. So as I alluded to, we'll be talking about Apple's A14 Bionic chip. We will talk about the Mars rover. We'll talk about some of the interesting things happening with security, AI, and semiconductor. And obviously, we'll touch base again with Tesla and their custom chip that is there in Tesla cars today. As a reminder, we are Skive. We build machines that feel. We are a San Francisco and London-based startup, and we are indeed hiring. So if you're interested, please reach out to us. We are on LinkedIn. We are on Facebook. Please feel free to reach out to me directly if you like. My email is aditya@skive.it. I will see you next week. Bye.